go get a calculator. If you don't have a calculator, go get a calculator. Alrighty. So today we are talking about continuous compounding. What do you think when you hear the word continuous? Over and over again. What did you say, Adriana? To repeat. So if it's continuous, does it ever stop? No, it doesn't. Can you think of another word in math that we use when something goes on forever like that, never stops? Not constant. Infinite or infinity. Yeah, so something that's infinite goes on forever, just like continuous, right? Continuous or continuously means it goes on forever, it doesn't stop. So we're going to be learning a new formula today. We've learned how to find the balance of an account when the interest is found using simple interest. We've learned how to find the balance in an account when the interest is compounded by a certain number of compounding periods in a year, either daily or weekly or semi-annually or monthly, right? And today we're going to learn how to find the balance of an investment or an account if the interest is compounded continuously. So we talked before, the more times that your interest is compounded, the bigger that amount is going to be. Let's go ahead and take these out. Everybody take your music out, Steve. Looks like it was really good. No earbuds, take your headphones and put them on your desk. Thank you. If you get your phone still out, let's go ahead and make sure you drop it down in your backpack, not in your pocket. Okay, so continuous goes on forever. So we're going to learn how to compute interest on an account that is continuously compounded. So we're looking for that key word. Then we'll know if it says continuously compounded, we'll know to use our new formula. It's a continuously compounded continuously formula. We've already talked about continuous means to go on forever. If it goes on forever, is there a limit on how many times it will happen? No, it goes on forever. How can you calculate something if it never ends? Well, we can calculate things just like we calculate them, right? We'll do an example of one of those. And what does infinity represent? The same as continuous, right? It goes on forever, never, never. If you happen to see this symbol is an infinity symbol, right? It's sideways 8. It means it goes on forever. Okay. So when they asked us about how can you calculate something if it never ends? So this example says you have to walk across a room that's 64 feet wide, but you can only travel half the remaining distance at a time. So each time you travel halfway. So if this whole thing is 64 feet, our first jump is going to be halfway to 32 feet, right? You are drawing the rectangle. Yes. So now we're at halfway, 32 feet. So now we're going to go, we have 32 feet left, so we're going to go 16 more feet, right? So now we're at 48. So now what we have left, we have not 48 left. Anyway, we keep cutting it in half. We don't even have to know what the number is. We know that we keep cutting the distance in half. Half of 64 is 32. We have 32 left. Half of 32 is 16. Half of 16 is 8. Half of 8 is 4. Half of 4 is 2. Half of 2 is 1. Half of 1 is a half. Half of a half is 0.25. Is it ever going to end? No, we can just keep taking half of whatever we have. If you only take half of it, you never get to the end. Right? If you only take 3/4 of it, you never get to the end. So that's what we're talking about here. When we say, how do you calculate something that you never get to the end of? It's continuous. We just keep approaching the end, but we never get to the end. but we never do. And there's nothing here, I don't know why I did the box, because you guys have all this in on your sheet. So just underline what I asked you to underline, okay? So this is the same prompt as the question we just did, and we just need to make sure we acknowledge that we're taking that remaining distance infinitely more times and that it's never going to end, right? We're going to keep walking towards them. We're going to be so close to that wall each time that technically we'll never get there. We just keep creeping up and creeping up and creeping up and never get there. Does that make sense to everyone? So we're approaching that distance or that spot, we never get there. And the conclusion is that we can add an infinite amount of numbers and get a finite sum. So all the halves that we take, if we do it an infinite number of times, it is really eventually, in theory, it is 64. In practice, we would never get there. All right, so we're going to do a couple of examples where we can see how these computations approach infinity. This has been more of a struggle throughout the day than I thought it should be, because some of the kids don't know how to enter the stuff in the calculator. They don't know what the function means. We have worked in functions a fair amount this year, so I'm going to remind you what this function means. So we're going to complete this table where y'all aren't all going to do all the numbers. I'm going to assign each row one of the x's, okay, to plug in. So I'll explain to you what this function means. F of x equals, so we're going to take one of these x's and we'll replace the x here and the x here with that number. Does that make sense? Now this says x squared, so whatever you replace, you're going to square it, then you're going to add it to 3 times that same number you're plugging in for, then you're going to add that to 5. Does that make sense? Okay. So J's row, y'all are going to, your input is 100. Sam's input, Sam's row, so that's this row right here, where Coley, Reagan, Sam, Jonathan, Hunter all are, that, your input is 1,000. Eden, Faith, Ayana, Quentin, yours is 90,000. Tristan, McKinney, and Nishad, yours is going to be 900,000. Tiana's row, Tiana, Stone, Luke, and Maxwell, you're going to put in 60 million. Now, you guys are doing 900,000 and 60 million. Just leave them in your calculator, don't write them in your table, because we're going to round those a little teeny tiny bit. Okay, you're going to get a funky looking number. Yeah, interesting, huh? Because these calculators will give you an answer in that form. Robert, what did you get?
I got 10,305.
Yep. Jonathan, what did you get?
3,022.
Yes. Eden, what did you get? You can just read me the numbers if you don't want to break it into millions and thousands. You should be able to, but you don't have to. Come on, just read me the numbers left to right. Nice. So, thousands, 100,000, millions, billions. 8,100,000, 100,270,000, and 5. All right, Tristan, what'd you get? That's right. Tell me what you got. Times to the 11th power, right? So his calculator gave him his scientific notation. We're going to round that a little bit. His is exactly right. We're going to round that. We're going to say greater than 8 times 10 to the 11th power. This is 8. You read all of that? Yes. All of these you guys are putting in your table. You just didn't have to do them all. Now these big numbers, you might want to try one of them on your, if you have a little number, you may want to try one of these bigger numbers. Maxwell, what'd you get?
I don't even know how to read this one.
That's right, just read me it. Just read the numbers, you don't have to read me the face value.
2.500015 times 10 to the power of 6.
Exactly. So we're going to write that more than, greater than 2 times 10 to the power of 15. The rest of these are in scientific notation because they're so humongous. You can't put all those decimal places on the calculator. Even the places that are on the calculator are rounded, right? The tendency for that first one would be 8.1 times 10 to the 11th power. The next one will probably be 2.5 times 10 to the 15th power. But all we're showing is how as those x's get bigger infinitely, the y's of the f of x's also get bigger infinitely. So they approach infinity. That's one of the phrases we want to practice using. As x approaches infinity, that means it's getting bigger and bigger with no limit, because there's no limit on the inputs here. So you can get as big, bigger forever, infinitely bigger. And the outputs will also get infinitely bigger. Maxwell?
So in this computation of the decimal point, do we not put decimal point 2? I thought
You
we
could.
said 2.5.
Yeah, you could. That's what I'm saying. Yeah, it would be a lot bigger, but we're just showing the growth here, so we didn't put it. But yeah, you're right.
Would you want us to do that on assignment?
It just depends on what they ask, but yeah, yeah. We took the 10th place, so. Sorry? Oh, you got it right there? Yeah. Yes. So the larger the x value of the input, the larger the y value, which remember that's the output. And another way to say that is as x approaches infinity, f of x approaches infinity. So they're not the same values, right? But they're going to go on continuously, forever and ever, with no limit to our inputs, no limit to our outputs. That's not going to be the case in all of these. Sometimes there is going to be a limit. It's going to infinitely approach a limit. And that's our next example we're going to see. You're right there, honey. You're supposed to be writing that, but I'm getting ready to change it. So I'll put it in. Alright? Okay. The next example. Let me remind you how to enter this on your calculator. This is f of x equals 6 times x minus 1 divided by 3 times x plus 2. So, there's a couple ways to enter on the calculator. You can start with no parentheses here, as long as it's equals. You have to know that the fraction bar needs division, right? But then you are going to need parentheses here, and you do have to hit equals again. So when I start, in fact, I'm going to do the easy one and let you guys, just to show you. So on my calculator, I'm going to do f of 100. That means I'm plugging in, my input's going to be the 100 here, okay? So on my calculator, I'm going to go 6 times 100. Everybody do it with me so you know how to do yours. 6 times 100 minus 1 equals, so everybody write down their calculation at 599, right? Divided by, left parentheses, 3 times 100 plus 2, close your parentheses, equals. You don't put that in your calculator. If that's what you said, you should spell that. I specifically did it so you guys would follow along with me. So that's what you should have gotten. Is that what you got there? When you look at your calculator, if that's not what you got, you need to ask for help so I can show you how to enter it. So you're going to stop talking over me. But I was talking, right? So figure your calculator out 3 times. Figure your calculator out 3 times. Do 6 times 100 minus 1 equals, divided by, left parentheses, 3 times 100 plus 2, close parentheses equals. Did you want to know on the board? Okay, that's how you do it. So now, Steve, whatever row you sit in, that's the one you're doing, okay? Jay, you're going to do the 50 million this time. Jay's row. Amina, Isabel, Brianna, Robert, Jay, y'all are doing 15 million. Sam, you're doing then 8 million. Faith, you're going to do 900,000. Tristan, you're doing 1,000. Uh-oh. Yeah, y'all are doing, sorry, 2 billion. Oh, y'all can have the 90,000. So y'all can have the 90,000. It doesn't, it's the same thing. That's what I want you to see.
I'm more likely to calculate correctly because it's not as good.
You are, and that is the beauty of this calculator though, because not all calculators allow you to see what is on that display, Maxwell, okay? That's why we use these, because you can see what you're entering. Think what number did I tell you guys have? 900,000. Amina, what number are you putting in? Isabel, what number are y'all putting in? 50 million. You're putting 50 million into the formula, Amina. Who is 1,000? All right. Michelle, what'd you get? You have to do it. Is that what you got? Hey. Oh, thank you so much. Okay, they must have just put them in. I wasn't there this morning. Thank you so much.
Yeah, they know you can see.
Okay, great. So Michelle got 1.98334444, right? So 90,000 Maxwell?
1.999998.48.
Yes. 900,000. We just did that one. Oh no, we did 900,000. 900,000. Who is 900,000? Faith, what'd you get? 1.6. No, Anna? 1.99999. Come on, 1.999998148. Yeah. So try it again, Faith, make sure you know how to enter it, okay? 8 million? Did you have 8 million, Colby? What'd you get?
1.9999979.
You have to write all of these. Oh, so what we're showing here is that these X's increase. I'm trying to do what you just asked me to do, so give me a second. I did. There you go. Okay, let's do one. You had 50 million. Did we already do that already? Good job. No, that's exactly right. And the last one we didn't do together, and we're going to all do that one together. So Megan, I'll send out you when you do it, okay? So get caught up with this, and then we're going to do the 2 billion in there. Sorry? Can I guess, please? I want to use my context clues. Sure. Is it 1.99999999996? Nope. Oh, man, okay. Close then. All right, so now if you're done, you got everything filled in, y'all try the 2 billion. 2 and 9 zeros. Ooh, this is pretty nice. Not going to be a formula. Nope. Look at the pattern. It's going to be an up and down. You got it on your worksheet, bud. You got it in your notes. So if you'll notice, each time Oh, she's showing me. These things are gonna be all 9, so let's try it.
I don't think it is. It's gonna be at least a 6 or a 7.
Try it. Use your calculator, try it. It's 2 billion in it.
Y'all trying to talk my feet.
Did you do it already?
Wait.
Are you gonna put it in so I can see what I do it? Yours. Did you put it in there, or are you just taking our word for it? Did you put it in the calculator, or are you just taking our word for it? Okay. Kristen?
Good. Can I just put, to repeat it, please? 1.9.
That's what, okay, normally you could, but I want you to put the 9s because I want to show the difference. So we're watching the progression of the number of 9s, but that is proper notation, but I want you to draw your 9s there. I like it that you remembered that and that you knew that, but it's much more effective, it's dramatic to see past the 9. So you can see here, it's approaching the number 2. But we've gotten so big, is it ever going to get to 2?
Yes, it will.
It definitely won't. You can put in 10 million, you can put in 100 billion. It's never going to get to 2. It's going to approach it, it's going to just increase the number of 9. Because that is the continuous growth here. It's going to continually grow, it's going to continually approach 2, because it doesn't have a limit. It's going to limit at 2. It's never going to get to 2, and that's what we're going to write for this one. As x approaches infinity, f of x approaches 2. So the last one was, as x approaches infinity, f of x approaches infinity, because there was no limit on inputs or outputs. But here you can see the pattern. It's never getting to 2. If it were going to be at 2, it would have been at 2, certainly at 2 billion. Right? What's going to happen is you just keep increasing those 9 to the right. 1.9 is 1 and 9/10. That's bigger than 1.99, which is 1 and 99 100. Which is bigger than 1.999, which is 1 and 99 1,000. Right? So, well, I take it back. It's smaller than 1 and 999 1,000. They're the opposite. It's getting bigger, but it's never going to get to that 2. Y'all caught up? So now, as these values approach infinity, we're going to start using what we call an exponential base. As values of x approach infinity, f of x approaches what is called the exponential base. And we're going to be using, this is an actual number, an irrational number like pi, an irrational number, the decimal place is never in, this one has a pattern, pi doesn't, but, anywho, what we need to know is how to enter this in our calculator. So that's what we're going to talk about right now, maybe. I can maybe keep it down. Alright. So we are going to, I'm going to show you how to do the calculator. So right now you're writing calculator. It's the E of X button. And to find it, look below the second button. We're actually going to use the second button, but right now, write that, and then we'll look at the second button and look 2 buttons down. The second function of the LN button is E of X. And that is the exponential base. You see right there, the purple one? So to use that button, we have to press the second button and then the LN button. And that will give us here, and when you do, it's gonna pop up with a less parentheses, you're gonna put in whatever value for your power, close your parentheses and hit equal. Did you write it there? You can write second and LN. Second and LN. That way if you forget how to find that button, how to use that button tonight on your homework, you'll have it in your desk.
I don't have a calculator at home.
What kind of phone do you have? What kind of phone do you have? There's the next button on this. I don't know what I'm telling you, but okay. You can use your phone at home, you just can't use it here. You do need to learn how to use these calculators, because these are what you're
Well, when I'm at home, my phone be dead.
Okay, well, I can't help you then. Here we go. That formula is illegible, so I'm going to rewrite it. But this is a continuous compounding formula, and it's A equals T E to the R times T power. Not pi, it looks like pi up there. Yeah, I know, it looks like pi, that's why I rewrote it.
That's what it said.
It looks like curve, yeah? So that can help you, you might remember it that way.
Yeah, A equals curve.
A equals curve. Alright, what do we, so some of these are exactly the same thing, the A, the T, the R, the T. We should know what all those are. What is the A that we've been using? What does A stand for in the formulas we've done before? So someone, y'all can get your notes out and look it up. I mean,
I think I do have my notes.
you don't remember what the A stands for.
Oh, annual compounding.
No?
No. A equals, oh, starting investing early. No. Oh, wait, no, that's the wrong one. Hold on, I'm gonna get it, I'll tell you. A equals,
The ending balance, guys. I would think we should be able to remember that. We've used it a fair amount. What's T stand for?
returning
Oh, thank you, beginning balance.
yeah.
What does the rate R stand for? It's the rate. How do you write it?
You have to,
As a,
decimal.
and the T is
Time.
in years. There you go. All of these we've done. This is the only new one, and it's not, what happened?
What's up?
There you go. Exponential base is the other one. And we don't have to do anything except use the button on the calculator for that. There's not, that exponential base is not going to be in the problem anywhere. But we have to know when we see the word compounded continuously that we have to use this formula that has an exponential base in it. Alright? Y'all caught up with me?
I have a question.
Yeah?
Did we automate 64 feet?
No. I mean, you can, I don't care, but I didn't require it. Alright, so now we have an example that asks us to compound continuously. We need to know that means, so it says, if deposited $1,000 at 2.3% interest, compounded continuously, what would be your ending balance to the nearest cent after 5 years? So this is our formula. I would like to see you identify your A, your P, your R, your T. Notice I didn't put E there because E is just a button on your calculator. Colby, you ready this? We're looking for A, the ending balance, right? A is the ending balance. We just wrote that on the last slide, yep. So that is what we don't know. What is our P going to be?
1,000.
And what is our rate gonna be?
0.023.
Right, so we're gonna take that, divide by 100, and drop the percent symbol. What's our time?
5 years.
5 years, I can't see my yours. Okay, so now we're plugging into this formula. This is what we don't know, so we're leaving that. P is gonna be 1,000, R is gonna be 2.3, times 75. So this is what it should look like. So on your homework tonight, I need to see this, and then the answer. I don't have to see anything else. Now, to put this on my calculator, you literally, I'm going to show you what's in the calculator. It's 1,000, then the E button, and you do that second LN. When you do, it's going to pop up with the left parentheses, so you're going to put 0.23 times 5, close your parentheses, and hit equal. You have to be practicing using the calculator, guys. If you're not practicing using the calculator, you may not be able, you may know how to do the stuff or understand where to plug it in, but you gotta be able to get the right answer. Hey, Anna? That's not right. Try it again. Clear it out. You don't have to put parentheses, you don't have to put time or anything between the 1,000 and the E. What'd you get, John? What'd you get, Robert?
Oh, I'm writing it down, sorry.
What'd you get, Jonathan? Yes. What'd you get, Iana? Yep, that's right. So rounding to that hundredth place, the nearest tenth. So you should get 1121.87. That is what it is. Put 0.26. But you rewrote it down there. Oh, my bad. You're right. I forgot my zero in there. Yes. Okay. The next slide, we're going to show you the difference in the growth for simple interest, compounded, some number of compounding periods, and then compounded continuously. Okay, and we're going to have to speed up because we have 10 minutes. Mark, set, go. All right, so here's the deal. The principal, or beginning amount, the rate, and the time are all the same. So let's go ahead and identify what those are. So the P, beginning amount, is 10,000. So it'll be the same for all the problems. The rate, 0.0185, is going to be the same for all three problems. The time is going to be the same for all three problems. And that's how we're going to be able to see how the method of compounding affects your output, or the value of the ending balance. So in this first example, they want us to find the ending balance after 3 years using simple interest. So when we see this, we have to know that we're going to use this formula to find the interest, and then it's going to be the interest plus our beginning amount. That's how we find our ending balance. So we're going to use that formula. We've already labeled our P. We've already labeled our rate and our time. So what you do is plug it in. You should be practicing using this calculator, but I'm not slowing down because we're cutting it close. The interest is $555. Is that the ending balance? Is that our answer?
Yeah.
It's not our answer. Remember we just said it's the interest plus the beginning amount of beginning balance. So it's 10,000 plus the interest. $10,555. Now the next one, exactly the same data, but it's compounded daily. So we have to know when we see compounded daily or semi-annual or monthly or weekly or bi-weekly, we have to know which formula we're using. We're using this compounding formula here. We know the P, the R, the T. What we don't know what we have not identified yet is our n. So based on the information given in number 3, what is the value of n? Yes. Compounded daily to know that n is 365, and we have enough information to plug into our formula. In this case, A is the ending balance, right? On your homework, just giving you a hint, on your homework, they're going to give you a compounding daily or maybe even a compounding continuously. But they're going to ask you for the interest. So remember, if they ask you for the ending balance, you use this formula and you're done. But if they ask you for the interest, you use this formula, then you take the A and you subtract the beginning balance, right? So whatever we get minus 10,000, that would be the interest on that money. But that's not what this asked here, so we don't have to do that. So now we're plugging in our calculator, making sure that we can get the right answer. So I will tell you that that's kind of a lot in your calculator. Some kids have liked going ahead and simplifying that, and I think it's the 1095. I think 365 times 3 is 1095. And now when you put in your calculator, you're going to put less parentheses. Oh wait, say it again. Oh, I forgot the 10,000. Yep, 10,000's got to go in front. Good catch. So 10,000. I don't think you have to put times. You can just put less parentheses. 1 plus 0.0185 divided by 365. Right parentheses for your caret. This arrow button is your exponent button, and then 1095. If you want to, you could enter with parentheses up here, but I think this is just as easy. What'd you get, John Luke? John Luke, what'd you get? Well, then I need you to try it, bud.
Can I say what
Hey,
I got? I got 109505555.
No.
Oh, man.
No. Eden?
10,577.68.
Yep. So, if you need help putting it in a calculator, 10,000 less parentheses. 1 plus 0.0185 divided by 365, right parentheses. Then use your exponent button,
Oh.
and then 1095, 1095, and then equals. And lastly, it says compounded continuously. So then we have to know that this is the formula we're using. A equals PERT, as Ayana said. We already know what our PR and PR are. All we're going to do is plug in. So remember, on your calculator, 10,000, second button, LN, going to pop up with the left parentheses. You're going to put in 0 or 0.0185 times 3, close your parentheses, and equal. Jonathan, did you try that one? John, look, you trying that one? Did you try this one? Which is that one? Yeah, try with the calculator. You're going to be able to do it with the calculator.
Can I say what I got? Oh, my God.
All right, so one more time. 10,000. The second button. The LN button. Y'all with me? It's going to pop up. You don't have to enter. It's going to pop up the left parentheses, and you're going to put .0185 times 3, and close your parentheses, and hit equal.
This is what I got. I got an every.
There you go.
What?
Yes.
How you gonna say
$10,570.69. See what you do it. Yeah, that's right.
Oh, no, I didn't say that.
We're going to do the rest of the notes at the beginning of class by me and you probably, but you won't turn those down. But you do have to do a worksheet is due tomorrow at the beginning of school. Starting my normal. You're doing all of it. You'll know how to do all of it. There's no new examples on there. 5 and 6 you're just comparing the outcomes we kind of talked about. Oh, here, I didn't write the amount for you guys in case you didn't get it. It's $10,570.69. It only goes up by 1 penny, but over time it would go up a lot more.